In this lesson, we are going to be talking about finding the volume of three-dimensional shapes using cross-sectional area, and this time we're going to be talking about triangles and semicircles. The previous video on this playlist will go over how to find cross-sectional volume with squares and rectangles. So when we are doing cross-sections as a follow-up to the previous lesson, the base of these solids is equal to f of x minus g of x. When we are doing these problems, we're going to look at three examples today. We're going to look at when the shape is an equilateral triangle, when it's an isosceles right triangle, and I have a little asterisk there. We're going to do that when the base is a leg of the right triangle, and then also when the cross-section is a semicircle. So in each of these cases, b, the base, is equal to f of x minus g of x. We're going to talk about how we can determine the volume of the shape by finding the area of each cross-section first. So let's say that we're looking at an equilateral triangle. When we're finding area of a triangle, we know that's 1/2 base times height. So the base we do know, right? So the base we know is the difference of the two functions, so f of x minus g of x. When we have an equilateral triangle, what we really get when we draw in that height or that altitude is we get a 30, 60, 90 right triangle. And if I use the ratios of special right triangles, we can determine that we know this is 1/2 b, right? The base here, the base of that right triangle. This is equal to b, and this is radical 3/2b. So now if I was finding the area of this triangle, it would be 1/2 the base times the height. And if I simplify that, I would get radical 3/4 times the base squared. So now that we know that the base is the difference of the two functions, f of x minus g of x, this is how we can get the area of that equilateral triangle. Radical 3/4 times f of x minus g of x squared. Now let's say that instead the triangle is an isosceles right triangle, and we know that the base is one of the legs of the triangle. So if I find the area of this triangle, we know these two legs are equal because it's isosceles. So I would say that the area is equal to 1/2 the base times the height, or 1/2 b squared. Now I'm going to write this in terms of our difference of functions, f of x minus g of x, and we see to find the area of this isosceles right triangle, we would have area equals 1/2 f of x minus g of x squared. All right, and then last we have a semicircle. So area of a circle is pi r squared, so area of a semicircle is 1/2 pi r squared. And if we look at this semicircle, the base is essentially the diameter. So when we're looking for the radius here, so let's say I draw in a radius, that's going to be 1/2 b. So let's say I substitute in that formula that 1/2 b for the radius. If I substitute that in and I start simplifying this, I would get 1/2 pi times 1/4 b squared. And if I simplify this, I'm going to get pi over 8 b squared. Now, if I scroll up, you can see where we are developing this formula, the area of this semicircle is pi over 8 times f of x minus g of x squared. Now, once we have the area, okay, and we know an equation to solve for the area, then what we're going to do is we're going to use that to calculate the volume. So when the cross-sections are drawn perpendicular to the x-axis, the volume is equal to the definite integral from a to b of the area function, a of x dx. And when we are instead drawing the cross-sections perpendicular to the y-axis, everything is now in terms of y. So our bounds of the integral are going to be y values, and we're looking for the area in terms of y with dy at the end. All right, so let's take a look at an example. So number 1 says the base of a solid is bounded by f of x equals 8 minus 2x and g of x is 0. We're going to find the volume of the solid where each cross-section is a semicircle taken perpendicular to the x-axis. So we know that it's a semicircle, so what I'm going to do here is I'm going to first just write the area formula from above. So we know that the area is equal to pi over 8 f of x minus g of x squared. So either you would have to memorize that idea, or you could draw a semicircle and come up and basically derive the formula like we did above. Now we know the volume is the definite integral. And in this case, it's going to be from 0 to 4. If I look at my picture here, you could see those are our bounds of the area function. So what I'm going to do is I'm going to plug in here pi over 8. And then our upper function was 8 minus 2x. Our lower function is just the x-axis, so 0 squared dx. And now we would basically calculate this. So we could do this by hand, but I am going to use my calculator. So I'm going to type this into my calculator using Math 9. And when I do that, I get the volume is 33.510. Okay, for number 2, we're given the base of a solid that's bounded by x equals 0, f of x equals ln of x, and g of x equals x minus 5. So I'm just going to color code a little bit here. So we have the natural log function and the line. So we can see that the upper function is going to be the ln of x one. And then let's see what we have to do. So A says write, but don't solve an integral that expresses the volume of the solid, where each cross-section is an equilateral triangle taken perpendicular to the x-axis. So what I'm going to need here for this problem is I'm going to need to know what these bounds are. So I can see that this is 0, -5. This one, though, is likely to give me a decimal because we're looking where ln of x is intersecting the line. So what I did off to the side before the video is I found these points of intersection using my calculator, typing 1 into y1, 1 and y2. Okay, and then again, finding the intersection. All right, so now that I have that, my bounds are going to be my x values. So the bounds for the volume are going to be 0, and then we're going to use the 6.9368,474. Okay. Since we're doing equilateral triangle, it's going to be radical 3 over 4. The upper function minus the lower function squared dx. Now, when we look at part B, though, it's a similar question, except now we're taking the cross-sections perpendicular to the y-axis. So that really means I'm going to be doing the right function minus the left function. So what I'm going to need to do first is I'm going to go to the top here where we have these two functions. If this is y equals ln of x, if I solve this for x, I'm going to get e to the y is equal to x. Over here, if this is y equals x minus 5, when I solve that, I'm going to get x is equal to y plus 5. So when we are doing perpendicular to the y-axis, we want everything in terms of y. So my volume is going to be equal to the definite integral, and now we're going to use the y values. So -5 to 1.9368,474. We're still going to do radical 3 over 4 in front because we're still doing equilateral triangles. And then what we're going to do here is we're going to do our right function, which is y plus 5, minus our left function, which is e to the y squared dy. Okay, for number 3, the base of a solid is bounded by f of x equals x squared minus 6x plus 3, and g of x equals -2x plus 3. We're going to find the volume of the solid where each cross-section is an isosceles right triangle, where the base is a leg of the right triangle, taken perpendicular to the x-axis. All right, so first I'm going to see and look at my picture here, and I can tell these 2 points of intersection from the graph are 0, 3, and 4, -5. So that's going to help me when I go and set up my bounds in a second. So let's just review for area of an isosceles right triangle. We talked about earlier in the video that that's 1/2 f of x minus g of x squared. Now we're going to plug that into the definite integral from 0 to 4. And we can see here that my upper function is the line, so -2x plus 3. My lower function is the parabola, so x squared minus 6x plus 3. And that's going to be squared dx. Okay, from here we can go to our calculator to evaluate this. So you could use Math 9 to type it in. I have already done that. And when I did to 3 decimal places, I got 17.066 as the volume of the solid. Okay, for number 4, the base of a solid is bounded by f of x equals negative e to the x plus 6, and g of x is equal to x squared. We're going to find the volume of the solid where each cross-section is a semicircle taken perpendicular to the x-axis. So let's recall again that the area of the semicircle would be pi over 8 times f of x minus g of x squared. And then what we're going to have to do is we're going to plug that into the definite integral, but we're going to have to find the bounds. So I've actually gone ahead already and found the bounds. So if you need to pause the video to verify these and make sure you know how to do them, you can. But basically what I did on my calculator is I plugged one function into y1, plugged the other into y2, and then I found the intersections there. So in this one, we're doing perpendicular to the x-axis, so my bounds are going to be the x values of those points of intersection. So the lower bound is negative 2.43148. The upper bound, 1.3977805. And now we want to substitute our area in here. So that's going to be pi over 8. My upper function is the exponential, so f of x, so negative e to the x plus 6. We're going to subtract the lower function, which is x squared. We're going to square that whole thing, dx. Then I'm going to go to my calculator. I'm going to plug this into Math 9, and when I do that, we should get 21.717 as the volume.